We've already seen one way to define multiplication of two vectors, namely the scalar product, also called the dot product. In fact, we saw three equivalent ways to define it, one geometric, arising from the law of cosines, one arithmetic, and one physical. In this video, we'll explore another way to multiply two vectors. In fact, we'll again see three equivalent definitions. This way of multiplying vectors, unlike with the scalar product, will result in a vector. To motivate why we would want to make this product a vector and not a scalar, we'll start with the physical definition. Let's consider a force that's acting on a rotating bar, as with a bicycle pedal, for example. Let's suppose that the bar is rotating around this point, and we'll represent it by the vector u. We'll represent the force by the vector v, which is acting on the end of the bar. We'll move v to here, so we see the familiar picture of two vectors whose tails are aligned. The force vector v could be pointing in any direction, but the only part of that vector that affects the rotation of the bar is the component orthogonal to u. Let's call it w. We're simplifying the situation a bit by ignoring things such as friction. We'll define the torque, or more accurately the magnitude of the torque, as the product of the magnitude of the position vector u and the magnitude of w, which we can write as the magnitude of u times the magnitude of v times sine of theta. We want to do a bit more, though, since we also want to indicate the rotation that would result from this force. In the case of this picture, w is pointing in a direction indicating that the position vector is rotating clockwise. We'll define the torque vector to be a vector along the axis of rotation. More specifically, the torque vector, which we denote u cross v, is this vector, where n is a unit vector orthogonal to both u and v, such that when u and v are oriented like this, the torque vector points away from u. If instead u and v are arranged in this way, then the torque vector points toward u, but has the same magnitude as before. To help us see this, let's suppose that u and v lie in the xy plane as in this picture. Then u cross v points up. The order matters, so if we switch the order of the product, then the result points down. We define the vector product, also called the cross product, of u and v to be the torque vector. Let's note a few properties that follow immediately from this definition. First, the vector product is a vector. Second, the vector product, unlike the scalar product, isn't commutative. In fact, it's anti-commutative, meaning that u cross v is negative v cross u. Third, and this time just like the scalar product, the vector product of au and bv is ab times the vector product of u and v. Fourth, if u and v are parallel, then the vector product is the zero vector, which makes sense given that a force parallel to the position vector of a rotating bar wouldn't move the bar at all. Let's now look at a second method of defining the vector product, this time motivated by geometry. We know the formula for the area of a rectangle, which is just the product of the base length times the height. If we represent these sides with vectors, then the area is the product of the magnitudes. Of course, the vectors can form any parallelogram. The area is still base times height, but the height is the magnitude of v times sine theta. We're close to the vector product we defined in the context of torque. We don't have a vector yet, though. To make it one, we can extend what we have to tell us something about the relationship between u and v. In the case pictured here, the vector product points toward us. As we saw with the scalar product, definitions such as the ones we've seen so far aren't great for finding products of vectors given in terms of x, y, and z components. For that, we generally want to use our third definition, which, remarkably, is equivalent to the definitions we've just seen. We define the vector product of u and v to be this vector. Those of you who've seen matrices before might recognize these components as determinants. For those of you who haven't seen matrices, let's take a moment to talk about them. A matrix is an array of objects, each of which can be identified by its row and column position. For example, the element A sub ij is the element in row I in column j. The determinant of a 2 by 2 matrix, that is, a matrix with 2 rows and 2 columns, is this. The determinant of a 3 by 3 matrix is this, which is in terms of 2 by 2 determinants. Finally, the vector product of u and v can be written like this. I encourage you to look back at the original formulation of the third definition and convince yourself that it's equivalent to this determinant form.